Hello everyone, welcome to this lecture series on linear systems theory. So, continuing on our week 5 discussion, so we started off of defining equilibrium points and characterized several notions of equilibrium point depending on whether trajectories around equilibrium, they converge to the origin, they go away from the origin, there could be periodic orbits, and all this were related to the nature of eigenvalues, and we did this with quite some detail in second order systems where the eigenvalues could be real with both of them stable, one unstable, and several of them including complex eigenvalues and zero eigenvalues. So, we will today look at two important concepts. One is which is essentially seen in the context of nonlinear systems and also in the linear systems a bit. That is the phenomena called limit cycles, and then we will go about looking at linearization of nonlinear systems. Okay, so just to begin with, the concept of limit cycles. So, first let us define what is the definition or what is the concept of an oscillatory behavior. So, a system is said to exhibit an oscillatory behavior when it has a non-trivial periodic solution, that x at t plus t is x of t for all t greater than 0 and from for some capital time t greater than 0, which is called the period. I am calling this non-trivial because so I would want to eliminate constant solutions. Even though constant solutions also exhibit this behavior, they are just constant for all time. So, they would definitely be satisfying this thing here. Okay, so in the phase plane, if I am just looking at non-trivial periodic orbits, this would of non-trivial periodic solutions, this would appear in the form of a closed trajectory, a circle or an ellipse. So, just to recall, the earlier lecture of this week. So, this would correspond to system which just had eigenvalues of the form plus minus j beta, complex eigenvalues where the real part is 0. So, the origin of the system was defined, the origin or we call this the equilibrium earlier. So, the equilibrium of the system is a center and the trajectories were closed orbits, and this essentially could also resemble like a harmonic oscillator, or if you just have LC circuit. So, this if there is some initial conditions, then this will always be oscillating around its equilibrium point. However, this linear oscillator is usually non-robust, which means that okay, so slight perturbations could add some value to the real term in the complex eigenvalues, and once this is true, say if alpha is less than 0, then the orbits will no longer be periodic, but if alpha is less than 0, they might just maybe spiral to the origin depending on the values of alpha, how large and small they are and so on. So, a slight perturbation will make it non-robust. Not only that, I mean, so this could be in terms of some resistances which correspond to the wires which connect the circuit and so on. Not only that, its amplitude is also depending on its initial conditions. So, if I start very close to the origin, so this will just be my amplitude. If I start here, this will just be the amplitude, right. So, the amplitude depends on the initial conditions. If it is close to the origin, the amplitude will just be very small for all times t greater than 0, and similarly if it is far from the origin. Okay, so, does there exist similar behavior in the nonlinear case, and in such a way that they could be structurally stable? So, I call this structurally unstable because not because the system is could be unstable, just because the existence of limit cycle can just disappear with some small perturbations, right. It might just, so I am just, if I talk in terms of poles and zeros, so these are my poles, a slight perturbation in the system might just push the poles say to the left, and once they are slightly to the left or slightly to the right, the limit cycle or the closed orbit no longer exists, right. So, okay, so what happens when I go to a nonlinear system? Okay, so I have this on R2 this dynamics. Okay, I think there should be a minus here. Okay, sorry for the typo. So, on R2 I have the dynamics x1 dot is x2 plus x1 1 minus x1 square minus x2 square, and similarly for x2 dot. Okay, what is interesting to see here is the following. So, when x1 square plus x2 square is 1, so these two terms go away. So, I have x1 dot is x2, x2 dot is minus x1, and this again corresponds to equilibrium point, which is a center, right. So, you will have closed orbits of this form. Okay, what is the difference between what we were looking at in cases like this and this is the following. Okay, so I have, so this is how in general the phase portrait would look like. So, I start from here, the phase portraits would go and converge to this closed orbit or the limit cycle in this case. Okay, so if I am at the origin, I start slightly away from the origin and I would still converge to this blue circle here, which is the limit cycle of the system. So, in summary, any non-trivial solution starting inside the circle or outside the circle will converge eventually to the circle. People familiar with circuits would have heard about the van der Pol oscillator, right. It's a nonlinear circuit with dynamics given by the following equation. Okay, I will not really discuss about the construction of the circuit, but we will be interested in its dynamics. So, if I draw the phase space, it will still exhibit a unique closed orbit, right, that attracts all trajectories starting outside the orbit. So, either here or here it will just attract to this blue closed orbit. So, just to show that, well, they need not necessarily be circle or ellipse, but they can take any kind of periodic form. So, this is a very important circuit or a system that has been studied a lot in physics. Okay, so this is just to give you a little illustration of subtle differences between linear systems and nonlinear systems, apart from the standard definitions of homogeneity and superposition. So, one big difference is in the existence of limit cycles. So, here you can just see that there is a unique limit cycle or a unique closed orbit, whereas if I go back to this situation where I have eigenvalues plus minus JB, there might just be family of limit cycles. So, start from initial condition, this will be my limit cycle, for some another initial condition, this will be my limit cycle, some another limit condition, this, and so on. Whereas here, give me any initial condition, I will just converge to the bluish circle here, or this blue closed orbit in the case of a van der Pol oscillator. So, that's a little distinction when I talk of closed orbits in the linear setting and also in the nonlinear setting. Okay, so that was about a little qualitative difference between linear systems and nonlinear systems, apart from the standard definitions that we would know. The next concept would be about linearization of nonlinear systems. If I say I start with this system in R2, x1 dot or r plus cross r plus, x1 dot is x1 log of x2, and similarly x2 dot is minus x2 log of x1 plus x2 with some initial condition, this one. Now, can I say that, well, this system is equivalent to this system? In a similar way, if I take a matrix A, then I do some P inverse AP with some similarity transformation, I would say that these two systems are similar to each other, that they are eigenvalues are similar and therefore their stability properties and so on are similar. Now, can I say that this system and this system are the same? Not only that, let me start with an example of a nonlinear system of this form, which is a simple normalized pendulum with the mass, the acceleration due to gravity, the length all normalized to 1, where d is some damping coefficient greater than 0. Can I write this system in this form? Can I transform this system into this form? Right. So, this is a linear system, right, linear system which has a equilibrium at q equal to q star. So, not only does this look like a linear system, but I can actually stabilize it to any point in the entire phase plane, right, starting from 0 to pi or 0 to minus pi. Okay. So, come back to the first example, right. So, how we go from A to P inverse AP is via a transform x equal to P inverse Z, or the other way, right, P times Z, just check this. So, this transformation will transform a system from x coordinates to z coordinates, and you can transform it into a diagonal form, a Jordan form, and so on. Okay. Now, here I just look at a nonlinear transformation now. Okay. So, Z1 is ln of x1, Z2 is ln of x2. Now, what is Z1 dot? So, if I compute this, so Z1 dot is 1 over x1, x1 dot. So, that is 1 over x1. What is x1 dot? Is x1 of x2. So, this is what is log of x2, that is Z2. Similarly, I compute Z2 dot is 1 over x2, sorry, 1 over x2, x2 dot, and I get a very nicely looking linear equation of this form. Not only that, even the initial conditions, they transform to the origin. So, one of the reasons that a system can be nonlinear is someone wrote it in the wrong coordinates. Now, here with a change of coordinates, I am not doing anything, no complicated math, or I am not even approximating the system or anything like that. I am just doing a coordinate transformation such that the system in the new coordinates looks like a linear system, right. It is a very simple linear time invariant system of the form x dot is ax plus bu. Okay. Now, in this example, now if I choose a input sin q minus q star, okay, maybe just add a plus v here. So, this will transform the system to a linear system of this form. I can write it in the state space form, right. So, this I can convert this second order equation into two first order differential equations. Okay, let's go back again to the first example and say, okay, the first process of linearization, this is not the first when you start learning linearization, right. This is just to give you an idea of linearization processes, is via a coordinate transformation I can change. So, this is a nonlinear coordinate transformation, and it will be invertible, and if I were to use purely mathematical terms, this map from x to z would be a diffeomorphism. Okay, we will not touch upon those concepts here. So, I can transform a system from a nonlinear system to a linear system via a nonlinear transformation. Now, does it always exist? Well, the answer is no. It exists if and only if certain conditions are satisfied by the system. So, I cannot do this always. So, this is not a part of this course of when can I linearize a nonlinear system via state transformation. That could be a part of some nonlinear or geometric control course. Similarly, here, so what did I do essentially here is that I used a state feedback, a nonlinear function of the state, to kill the nonlinearity. The nonlinearity here comes from the sinusoidal term, right. So, this essentially is also called feedback linearization. Now, can I do this all the time? If this was so simple that I could just kill the nonlinearity just by, so mathematically here I am just adding a sinus term to the input and it just the nonlinearity disappears. Now, can I do it all the time? Again, the answer is still no. There are some conditions that my system should satisfy, or the structure of the system should satisfy in order to accomplish this feedback linearization. So, there are several nonlinear examples in literature which cannot be feedback linearizable. Of course, that is not again our point of interest. Okay. So, what do we in generally learn so far, right, when we say start even with mechanics or circuits. So, most laws we learn through physics, right, the Newton's laws, circuit laws and so on, they are approximation of certain nonlinear relationships. So, in the week 1, the first lecture, we saw how P equal to mV was restricted to a certain range only, and similarly with inductors and so on. So, a natural way to study systems is by the following set of equations: x dot is f x u and y is some h x u. So, where x is in say some n dimensional state vector, u is some m dimensional input, y could be some p dimensional output. Okay. Now, so naturally I know that systems are nonlinear, even though I learn a lot of physics, a lot of circuit theory or mechanics through linear approximations of nonlinear systems. Okay. So, the questions that we will be interested is, can one analyze or retain some properties of nonlinear system via its linear approximation, and how to get that approximation. So, here I am not really doing an approximation, I am actually doing a proper transformation. This is not approximation, this is valid. So, in for a larger this is valid in much larger region of the state space than just around a small operating point. So, these are more systematic processes, but can we do something simpler just to suit our purposes at the moment and to also answer some really basic questions. Okay. So, let us go back to start with the setting of nonlinear setting x dot equal to f x comma u, and so the definition says the pair x star u star is called an equilibrium point if f, sorry, they should read f of x star u star equal to 0, or f evaluated at x star u star will just be 0. Okay. Now, so once I am at this point x star u star, I will always be at 0. Okay. So, let us say now I apply a slight an input to the system u star plus delta u t, and this is an arbitrarily small perturbation in the input away from u star, and similarly from the initial condition, right. So, so let us say the initial condition is not x star, but some small perturbation with x star. You can also look at it as just applying a small input u of delta u of t and see how it causes a small variation delta x of t. Okay. So, this is the assumption we make, right, that these variations are really small. Okay. Again, so in this case the corresponding system output, which was y of should be x. So, y which was h x star u star with these new conditions will be close to but not equal to the original output. Okay. Now, I need to check how much is the perturbation in x because of these two, what happens to x. So, initially x was just 0, right, for all t. If I start with at the equilibrium point, I will always be at the equilibrium point. So, when I apply these small perturbations delta u, so what is the change in x and what is the change in y, so, or in other words, how much are x t and y t perturbed by these delta x and delta u. Okay. So, so the definition, I will do a quick derivation of this, that the linear system delta x dot is a delta x plus b u, delta y is c delta x plus d u defined by these matrices. I will shortly tell you how to derive this. So, this system is called the local linearization of the nonlinear system around this equilibrium point. So, whenever we talk of linearization, we will talk of linearization around certain operating point, right. Okay. So, how do we derive these things? So, the input that I apply is u of t is u star plus delta u t, right. This is very close to the initial condition, but not equal to, right. Similarly, x of t is x star plus say some delta x, right. Again this is close to but not equal to x star. Okay. So, similarly, I will have a corresponding change in y. Y would be equal to h x star u star. This is the one at the equilibrium, but my y will be some y plus delta y. So, y of t here would be, or sorry, the change delta y would be y of t minus y at the equilibrium point. Similarly, the change in x would be x of t minus x star. Okay. So, we will now determine the evolution of delta x, and similarly we will do for delta y. So, delta x dot is from here is x dot, x star dot will be 0 because it is a constant. This is f x comma u. Now, how do this x comma u vary? They vary according to this thing x star plus delta x comma u star plus some delta u. Okay. Now, I can do a Taylor series expansion for this. Okay. Taylor series expansion around x star and u star. Okay. So, this will give me delta x dot is the partial derivative of f with x evaluated at x equal to x star, u equal to u star times delta x plus the partial derivative of f with u also evaluated at x star, sorry, u star and a delta u plus all the other remaining terms, which I will just call the higher order terms in delta x and delta u. Okay. So, this is called the Jacobian matrix also. So, you are actually differentiating a vector valued function. So, f here is a vector valued function. Okay. So, how to compute this? I will just do a little illustration, so that it is a little easier to understand. So, let us say I have a system in R2 would be f x1 x2, x2 dot is f2 x1 x2, right. So, this is x is in R2 and f is also in R2. Okay. So what is so this is like okay, in general we write this as x dot equal to fx, right, where x is x1 x2, f is f1 and f2. So, df by dx will be the following matrix: partial of f1 with x1, the partial derivative of f1 with x2, partial derivative of f2 with x1, partial derivative of f2 with x2. And similarly, if you have u, it will be the same, right. So this is how we compute the Jacobian matrix or the gradient of or the derivative of a vector valued function, and you can just extend it to n dimensions, right. So it's a simple straightforward extension. right. Okay. So, if I now go back, so I have x dot is delta x dot delta x dot is a times delta x, where a was df by dx. So, that is what is here, right. So, delta x dot is df by dx evaluated at a. So, this is a, this entire thing here, a times delta x. These are all constants, right, because you are evaluating them at particular points x star and u star. So, they will just be a constant matrix, and similarly here. So, this will be b times u, again it is evaluated at x star and u star, and so it will be a constant. So, this will be delta u. Okay. Similarly, I can do with the output equation delta y of t is y t minus y star, and I can just do it very similarly and then find out what is delta y. I'll skip that little derivation. Okay. So, C would just be partial of h with x, and D would be partial of h with u, all evaluated at x star and u star. Okay. It's interesting to see a little example here. Right? So, first is I just look at the equations of a normalized pendulum, and let us see what does the linearization tell us here. Okay. So, first I write this in the state space form. Q1 dot is Q2, Q2 dot is sin Q1 minus D of x2, again D is a damping coefficient greater than 0. So, the 2 points, equilibrium points of interest are 0 0. So, the downward position of the pendulum is an equilibrium point, and the upward position is also an equilibrium point, right. And then this will be my Q. Okay. So, any other would be just be a multiple of these values of 0 and pi. Okay. So, for example, 2 pi is also an equilibrium point, 3 pi is also an equilibrium point, and so on. So, these are the two equilibrium points of practical interest. So, to analyze the local behavior, we first look at its local linearization, that is I look the equations in terms of delta q dot is a times delta q. Okay. So, I just do the linearization of this. So, I will just quickly run you through this. So, the equations were q double dot plus sin q plus d times q dot is 0, or if I write it in the first order differential equations, q1 dot is q2, q2 dot is minus of sin q1 minus of d times q2. Okay. So, that is what is here. Okay. Now, let me compute the A matrix for this. A is df by dx evaluated at the equilibrium point. So, df by dx here is okay. So, df1 by dx1. So, x1 x2 are the q1 q2 here. So, this will be 0. So, I am looking at the partial derivative of this term with respect to q1, that is 0, with respect to q1, that is 1. Partial derivative of this term with respect to q1 will appear here as cos q1, partial derivative of this term with respect to q2 will appear here minus d. Okay. And now, I compute this at 0 comma 0 and pi comma 0. So, these are my two equilibrium points. Okay. So, at 0 comma 0 I get my equilibrium point, so my A matrix to be something like this, okay, and its corresponding eigenvalues can be computed to be like this. So, when D is less than 2, the eigenvalues are complex conjugate, and hence the equilibrium is a stable focus. Okay. So, similarly, when D is greater than or equal to 2, there will be real, and these eigenvalues, both of them will be negative. The equilibrium point here would be called a stable node. When D equal to 0, the eigenvalues are imaginary, and the equilibrium point will be a center. So, physically this would mean that okay, I just have a pendulum which is stable at its downward position. I just perturb it slightly, it will come back to its original configuration as long as D is greater than 0. How fast or how slow will it come back will again depend on the amount of damping in the system, right. So, this is a clear relation to what we studied, and also physically this is also intuitive, right, that the downward position is always the stable position. Okay. And d equal to 0, which means there is no damping, a small perturbation, I will just keep on oscillating around the equilibrium point, right. Okay. Now, interesting thing will happen when I am looking at linearization around the point pi comma 0, in which case my A matrix takes this form and eigenvalues are like this. Okay. So, for d greater than or equal to 0, the eigenvalues will be of real and opposite signs, and the equilibrium point will be a saddle point. So, I can just quickly compute for 0, 1, 1, 0, with d equal to 0, the eigenvalues would be plus and minus 1. Okay. Now, let's what it turns out is pi comma 0 is an unstable equilibrium, because it will have eigenvalues which are plus and minus 1, and this is a stable eigenvalue. So, if I roughly plot the phase space here, so this would be 0 comma 0, pi comma 0, minus pi comma 0, and so on. Around here the trajectories will tend to the origin in this way, either they will spiral or depending on the values of g. Around here the trajectories will diverge away from the origin. Around here also trajectories will diverge away from the origin, they will meet here and then come back here. Trajectories from here will go from the origin and again so on. So, locally what I see is that if I compare with the nonlinear phase space, locally around the equilibrium point the behavior is the same, right, and this is also little intuitive, right. So, if I take a pendulum on the upward position and I give a side perturbation, it will just come back here, right. So, that means that this is an unstable equilibrium. So, the definition of stability which we will do in the next week's lectures more formally is a slight perturbation from the equilibrium point. Does it, if the system comes back to its original configuration, then it is a stable equilibrium, otherwise it is an unstable equilibrium. Also, stability we will talk essentially in terms of equilibrium points only. Okay. So, this was a little hint about or little introduction to linearization around an equilibrium point, a local linearization. So, you can for just exercise as an exercise check these two examples here which we began with. So, here origin is an equilibrium point, just check the linearization around the equilibrium or the origin and check what kind of what is the characteristic of this equilibrium in terms of a center, a saddle point, a stable node, unstable node, and so on. Similarly, you can do for this. You can also play around a bit with mu being equal to 0, mu less than 0, or mu greater than 0. So, it is just a very basic mechanical exercise. So, I will not really do problems on this. This is just computing basic derivatives and then computing those eigenvalues, and mostly we will just deal with second order systems. Okay. So, that concludes the lecture on linearization. In the next week, that will be a very comprehensive discussion on stability, types of stability, from asymptotic stability to just stability to exponential stability and so on, and also look at some how do we verify stability of system. When I look at transfer functions, I just say, well, compute the poles. If the poles are to the left, then the system is stable. If the poles are on the imaginary axis, then there are certain conditions that need to be checked, and so on. So, are there techniques, what are the techniques that we encounter while we study about stability of systems in the state space domain, both in the continuous time and discrete time. So, that will be coming up in week 6. Thanks for listening.